In this video, we present the FAST-Hex, a micro-aerial hexarotor that allows to seamless transit from an under-actuated to a fully actuated configuration with only one additional control input, a motor that synchronously tilts all propellers. The FAST-Hex adapts its configuration between the more efficient but under-actuated coplanar rotors to less efficient but full post-tracking non-coplanar rotors. We will first present the mechanical structure of the FAST-Hex and later in this video demonstrate 3 experimental results. For better understanding, we'll show the mechanics with the help of CAD images. The main structure of the FAST-Hex is a regular ring, on which 6 motor towers are mounted that can actively tilt the rotors. The ring structure hosts a set of axles that are connected via universal joints and are actuated by a single servo motor. In the base of every motor tower is a warm drive giving a high gear ratio, minimal backlash and self-blocking capabilities. Via a lever mechanism, the rotation is transmitted to a swing that hosts the rotor. To allow opposite tilting angles of neighboring rotors, we use inverted warm drives in every second motor tower. All electronics, including an IMU, a flight controller and the speed controllers for the rotors, are located in the center of the ring, decoupled from vibrations caused by the spinning propellers. In this experiment, we command the FAST-Hex to track 2 trajectories with independent position and orientation profiles. The position trajectory follows a horizontal sine wave, while the orientation trajectory is constantly horizontal. Starting from a 0 tilting angle, we will increase the angle over time to 30 degrees. Our controller works seamlessly in the under-actuated and the fully actuated configuration. It prioritizes the position tracking over the orientation tracking. The larger the tilting angle, the more the platform can realize an arbitrary force vector and track simultaneously a position and orientation trajectory. If the required force vector cannot be implemented, the controller adapts the reference orientation such that it complies with actuation constraints. In this experiment, initially the controller has to significantly alter the reference trajectory to output a trackable desired trajectory, as the platform is under-actuated, making the attitude trajectory fully coupled with the position trajectory. In the plots, we depict the reference and actual body position, the tilting angle, the desired trajectory, which is an output of the controller and that gradually approaches the horizontal reference trajectory, the actual orientation, and the motor spinning velocity. In the second experiment, the position trajectory is constant, while the roll angle follows a sine wave with a peak angle of 6 degrees and a frequency of about 0.1 Hz. The pitch and yaw angles remain constant at 0 degree. A standard coplanar multirotor is not able to track a trajectory for roll and pitch while remaining at a fixed location, as multidirectional forces would need to be applied. The trajectory is therefore unfeasible for an under-actuated vehicle. As in the previous experiment, the tilting angle is linearly increased from 0 to 30 degrees. As the platform is initially under-actuated, the controller is required to adapt the reference attitude trajectory into a trackable desired trajectory. As a consequence, the controller outputs a desired trajectory that is basically constant and horizontal. As soon as the feasible horizontal body force is large enough, thanks to the increasing tilting angle, the FAST-Hex gradually starts to track the reference attitude trajectory. Starting from a tilting angle of 25 degrees, the reference attitude can be fully tracked. The lateral forces required to track the desired rolling motion can now be completely generated by the propellers. The plot in the lower right corner displays the evaluation of feasible forces in body frame. It becomes obvious how the volume of feasible forces increases from a line to an increasingly larger volume while the tilting angle increases. In this last experiment, we present the response of the FAST-Hex and of its controller with respect to external force disturbances. To do this, we attached a rope close to the FAST-Hex center of mass and apply to it a constant force of 4.2 Newton. In this way, we in example emulate the scenario of a constant wind disturbance or a contact-based inspection task. This experiment provides insights on how the controller in the FAST-Hex copes with disturbance during different configurations. Also in this case, we linearly increase the tilting angle through the test. During the first phase, while the FAST-Hex is under-actuated, the desired pitch angle needs to diverge from the reference pitch angle. The FAST-Hex has to tilt by approximately 6.6 degrees to reorient the unidirectional force vector. As soon as the tilting angle increases, the pitching angle decreases too. Once the tilting angle is increased beyond 25 degrees, the platform is able to fully resist the force disturbance while tracking the original reference orientation. Interestingly, the position tracking error decreases with an increasing propeller tilting angle.